Hello and welcome to this lesson on latent heat, which is part of the thermophysics topic in AQA A-Level Physics. So in today's lesson we're going to look at understanding and calculating latent heat. So if we have been successful and learned in today's lesson, we should be able to detail the ways in which internal energy of a system can change. We can define and describe what the latent heat of a substance is, and then finally we can calculate values based on the latent heat of a substance, which links into the following part of the AQA A-Level Physics specification, 3.6.2.1 Thermal Energy Transfer. So in the particle model we should consider all forms of energy stored in the particle structure. So you've got the average kinetic energy of a substance, which is linked to the temperature, and there's also the potential energy stored in the substance due to the forces of attraction between the particles in the substance. So there's a potential energy stored between the particles in any substance, which is due to the intermolecular forces of attraction between the particles and the chemical bonds. There's also a kinetic energy store found in the particles of a substance due to the particles moving. Now together these two energy stores are referred to as the internal energy of the substance. So internal energy is equal to the kinetic energy plus the potential energy. But to calculate the internal energy of the matter of the substance, we've got to consider the kinetic energy of all the particles and the potential energy of all the particles. So to summarize, the particles within a substance all possess kinetic energy. This energy is due to their motion, whilst particles also contain potential energy due to the chemical bonds and intermolecular forces of attraction holding them together and the bonds within their nuclei. The sum of all these kinetic and potential energies found in each particle represents the body's internal energy. So the internal energy is the kinetic energy store plus the potential energy store. Now changing either the kinetic energy or the potential energy store causes the internal energy to change. So the internal energy of an object is the sum of the random distribution of the kinetic and potential energies of its molecules. So increasing either the potential energy store or the kinetic energy store or both will result in an increase in internal energy. Now just to clarify, these stores are internal to the system and are not combined with the external stores of kinetic or potential energy a substance may experience. Now, changing the kinetic energy changes the internal energy store, which will cause the temperature of the substance to change, whilst changing the potential energy store changes the internal energy store also, but when you change the potential energy store, the state of the object will change. So this leads to a fundamental law of physics, that the change in internal energy of an object is equal to the total energy transfer due to work done in heating. So placing work into a system will change either the potential or the kinetic energy store, which is the first law of thermodynamics. Now when applied to objects, the direction of the energy transfer is very important as it determines whether the internal energy goes up or down. So when a substance is changing state due to heating, the potential energy store of the object will increase in the change of state. So as work is done into the system, energy goes into giving the particles more potential energy to break their bonds and lower the forces of attraction, such as going from a liquid to a gas. Now this doesn't make the particles vibrate anymore because the kinetic energy store is unaltered. So when you put work into the system, it will cause the potential energy store to increase, which causes the objects to separate. Now, it's the same idea when going from a liquid to a gas. So if we've got the idea of particles constantly vibrating, eventually the particles have enough potential energy stored to overcome their forces of attraction to move away from each other and jolt past each other. This will cause a change in state. Now it's important to note that at this point most of the potential energy stored then changes to the kinetic energy store, so after that state interchange that potential energy store lowers. Now we can also look at the idea of when an object changes state due to cooling down. Well, when this takes place, the potential energy stored will decrease, because as work is done out of the system, the potential energy stored in the particles is lost to the surroundings. Now this doesn't make the particles vibrate more because once again the kinetic energy stores unaltered. So when work is done out of the system, you move into an even lower potential energy store. Now eventually the particles have lost so much potential energy stored, they succumb to their forces of attraction and will move towards each other, so they'll jolt together. So this will cause a change in state. Now when this happens, most of the kinetic energy store is changed to a potential energy store, so it means that after the state interchange, the potential energy store has increased. So let's just clarify, when work is done to the internal energy of a system, the energy can be used to change the average kinetic energy, so change the temperature, or change the average potential energy, change the state of the internal energy. Now in previous lessons we've considered changing the kinetic energy store, but now we're going to consider changing the potential energy store. Now it's important to note that for most objects in the internal energy, the potential energy store is larger than the kinetic energy store. Now again, if we change the potential energy store, we can change the internal energy. Changing the internal energy of a system is called doing work. So it's an important idea to consider. So let's consider what happens when we change the potential energy store of the internal energy of a system. So a change in potential energy store would result in a change of state. Now it's important to note that different substances require different amounts of work to be done to change them from a solid to a liquid to a gas, or any other state change. This is due to there being different forces of attraction between the particles given potential energy stores. So the forces of attraction are due to the size of the particles in the substance. This means that the mass of the particles affects the potential energy store. Now, in addition to that, the forces of attraction are different due to the different types of particles. This means that something called the latent heat capacity of a substance affects the potential energy store. So the work done required to change the potential energy store in the internal energy of a system is a combination of two factors. You've got the mass of the object and the specific latent heat or latent heat capacity. Now, delta Q represents a change in potential energy in the internal energy store and is measured in joules, whilst the mass is measured in kilograms, whilst the specific latent heat is measured in joules per kilogram. So L represents the specific latent heat, which is the energy required to change the state of 1 kilogram of a substance without a change in temperature. Now the more rigorous definition of specific heat capacity must now include without the change in temperature status. Now the specific latent heat of fusion is the energy required to change 1 kilogram of a solid into liquid, or vice versa, without a change in temperature, whilst the specific latent heat of vaporization is the energy required to change 1 kilogram of a liquid into a gas, or vice versa, without a change in temperature. Now the latent heat of vaporization needs more work to be done to be carried out compared to the latent heat of fusion, as the particles change position more going from a liquid to a gas, or vice versa, compared to a solid to a liquid. So this changes the forces of attraction more, so therefore more work is needed to be done. This is because the liquid and gas particle model are very different in configuration. So this means that there's a large change in the forces of attraction and more bonds are broken, so therefore there's a greater change in the potential energy store, giving a large latent heat. Whilst if you have a liquid to a solid, or vice versa, the liquid and solid particle models are not that different in configuration. So there's a smaller change in forces of attraction, so less bonds are broken, and the potential energy store changes less, so it gives a smaller latent heat. So this tells us that in fact that the latent heat of vaporization is a much larger value for a substance compared to the latent heat of fusion. So just to clarify, we define the latent capacity as the energy supplied to a substance to change the forces of attraction to make the substance change state. So the specific latent heat capacity is the energy needed to make 1 kilogram of a substance change without a change in temperature. So the latent heat is the link between the potential energy store change and the resultant change in state. So the larger the specific latent heat, the more work is needed to be done to change the state of a substance. So the larger the latent heat capacity, the more potential energy which is stored as internal energy per state change. So if you consider two materials undergoing the same change of state, an object with a higher latent heat capacity or specific latent heat will store more potential energy per state change, so will have more internal energy. So this means if you have a high specific latent heat capacity, this means that the object with a larger potential energy store store and have particles with greater force of attraction will be the one with the higher specific latent heat. Now please remember that when the potential energy store changes size, there's no work done on the kinetic energy store in the internal energy of the system. So this means that when there's a change of state, there's going to be no change in temperature of the substance. This idea can be illustrated on a heating curve. So when a substance changes state, there's no change in temperature, which we can indicate on a heating or cooling curve by a flat line. So what happens is the energy goes into changing the potential energy store of the internal energy and not the kinetic energy store. So this tells us that this change in energy is hidden from the temperature observation, or it is latent, as latent is another word meaning hidden. Now we can identify a state change from a heating or cooling curve, like we said before, when there's a flat line, because when there's a change of state, there is no change in temperature, so the work is being done on the potential energy store. So when there's a change in temperature, there is no change in state. So you can see on this particular heating curve, where there are flat lines, there's a change in potential energy. Now you'll notice that when there's a change of temperature, we know that there's going to be no change of state, so as a result it's a change in the kinetic energy store of the object's internal energy, not a change in the potential. So you get either a change of temperature when your line is either going upwards or downwards, and you've got a change of state when the line is flat. So you've either got a change in the kinetic energy store, which is indicated by a change in the temperature, or you've got a change in the potential energy store, which is indicated with a change in state. Now when a solid is heated, work is done to make the particles vibrate more, which means that the temperature increases. Now at this point, because the temperature is increasing, the potential energy store of the solid remains constant, but the kinetic energy store increases. Now at the melting point, the particles don't vibrate any faster, meaning that the kinetic energy and the temperature are therefore constant. But the bonds that keep the particles in a rigid shape are broken, and the potential energy store increases. Now in liquid form, the particles are still in contact with each other, but can slide past each other. Now as more work is done, the particles vibrate more, so the kinetic energy store increases, but the potential energy store is constant. Now at the boiling point, the particles again don't vibrate or move any faster, meaning that the kinetic energy store and the temperature are constant, but the bonds holding the particles together are completely broken. Now what this means is that the temperature doesn't change, but the state does. Now this takes a lot more energy when this happens compared to melting, since all the bonds are broken. So therefore the latent heat of fusion is going to be less than the latent heat of vaporization. Now the same process is true if the substance is cooled down, because the physics of heating and cooling are identical. However, heating requires work to be placed into the internal energy of the system, whilst cooling requires work to be taken out of the internal energy of the system. So previously, we have stated that the internal energy is the amount of energy found inside of a system, made of two parts, the kinetic energy store and the potential energy store. But remember, the internal energy is a representation of all particles in the system. Now we can calculate the internal energy of a system by using the equation, the internal energy is equal to the kinetic energy plus the potential energy. Now the kinetic energy store can be looked at by thinking that a change in kinetic energy store is shown by a change in temperature, and this energy can be calculated by using the specific heat capacity, whilst a change in potential energy store is shown by a change in state, and this energy is calculated by the specific latent heat. But remember, it's only true when we consider all particles in the system. So we can calculate the change in the kinetic energy store by doing delta Q is equal to m times by c times by delta T, where c is the specific heat capacity. And we can calculate the change in the potential energy store by saying delta Q is equal to m times by L, where L is the latent heat. So we can therefore say the overall change in the internal energy is delta Q is equal to mc delta T plus ml, because you have your change in your kinetic energy store and you have your change in your potential energy store. Now because m is a common factor in both terms, we can factorize out m in the equation. So we can therefore say delta Q is equal to m times by c delta T plus L. So as a result, we can therefore work out mass quite easily. Now please remember that this equation is not the total internal energy of the substance, rather it is the internal energy change. Now let's just summarize what we've learned in today's lesson. So for a change of state, Q is equal to mL, where L is specific latent heat. Now if we've been successful and we've learned in today's lesson, we can detail the ways in which the internal energy of a system can change. We can define and describe what the latent heat of a substance is, and finally we can calculate values based on the latent heat of a substance. So thank you very much for watching today's lesson on latent heat, which is part of the thermal physics topic in AQA A-Level Physics. Thank you very much for watching and have a lovely day.